Welcome to Chapter 3 of the Introduction to Process-Informatics series. In this lecture, we will dive into the mathematical foundations of process modeling. We will explore linear and multiple regression, learn how to evaluate model performance using metrics like R-squared and root mean square error, and discover powerful techniques like partial least squares for handling complex industrial data. By the end, you will understand how to build predictive models that transform raw sensor data into actionable insights. Linear regression is the cornerstone of process modeling. The equation y equals beta 0 plus beta 1x plus epsilon captures the essence. We are finding the best straight line through our data points. Beta 0 is the intercept. Beta 1 is the slope that tells us how much y changes when x increases by 1 unit, and epsilon represents random error. The method of least squares finds the optimal parameters by minimizing the sum of squared differences between predictions and actual values. Real processes rarely depend on a single variable. Multiple regression extends our model to handle many inputs, y equals beta 0 plus beta 1 x1 plus beta 2 x2, and so on. This multi-input single-output structure is perfect for industrial settings where product quality depends on temperature, pressure, flow rate, and composition simultaneously. Each coefficient tells us the independent effect of that variable, holding others constant. How do we know if our model is any good? 3 key metrics guide us. R-squared, the coefficient of determination, measures the proportion of variance explained by the model. 1 is a perfect fit, 0 matches a constant mean predictor, and a model that does worse than the mean on held-out data scores below 0. RMSE, root mean square error, tells us the typical prediction error in the same units as our target variable. MAE, mean absolute error, is similar but uses absolute values, making it less sensitive to outliers. Always check all 3 metrics for a complete picture. Process data often suffers from multicollinearity, input variables that correlate strongly with each other. Ordinary regression struggles here, producing unstable coefficients. Partial least squares, or PLS, solves this elegantly. It extracts latent variables, linear combinations of inputs that maximize covariance with the output. These latent variables are orthogonal, eliminating multicollinearity. A key decision is selecting the number of components using cross-validation to find the optimal balance. Soft sensors are perhaps the most impactful application of process modeling. While hard sensors measure physical quantities directly, soft sensors infer difficult-to-measure quality variables from easily measured process data. Consider product purity. Laboratory analysis might take hours, but a soft sensor provides real-time estimates every second. Well-designed soft sensors enable tighter quality control and faster response to process upsets, making them essential for modern manufacturing. Building an effective soft sensor follows a systematic workflow. First, data collection from process historians. Second, preprocessing including outlier removal, missing value handling, and normalization. Third, feature selection using correlation analysis and domain knowledge. Fourth, model training with appropriate algorithms. Fifth, online deployment with real-time dashboards. Include a validation loop for continuous monitoring and periodic recalibration. Plan for model maintenance as processes evolve over time. Cross-validation prevents the trap of overfitting, models that perform brilliantly on training data but fail on new data. K-fold cross-validation divides data into K parts, trains on K-1 parts, and tests on the remaining part, rotating through all combinations. For time series data, use time series split to ensure you always train on past data and test on future data. The cardinal rule for process data: never let information from the future leak into training. When linear models do not capture the complexity of your process, nonlinear methods provide more flexibility. Random forest uses ensembles of decision trees to capture complex interactions and provides feature importance. Support vector regression with kernel functions handles nonlinear patterns elegantly. Gradient boosting iteratively corrects prediction errors, often achieving top performance. Choose nonlinear methods when linear model R² falls below 0.8, or when you know nonlinear relationships exist. Let us recap Chapter 3. Linear and multiple regression provide interpretable models for process relationships. Model evaluation requires multiple metrics, R² for explained variance, RMSE, and MAE for prediction accuracy. PLS handles the multicollinearity common in process data. Soft sensors transform these modeling techniques into real-time quality prediction tools. Proper cross-validation ensures our models generalize to new situations. In Chapter 4, we will put all this into practice with a real distillation column case study.